Right, question 3. Plastics which soften when heated are classed as thermosoftening plastics. That's fair enough. We didn't know this. This is one of these things that happens in the exam. They give you information that you've never heard before to make you, make you question your own knowledge in some ways. If you've done all your revision, you know your course, then you know that you shouldn't know about this stuff. They're just telling you about it. Okay, so polyvinyl chloride, PVC, is an example of a thermosoftening plastic and is used in the manufacture of clothing. The repeating unit of PVC is shown. There it is. There's your repeating unit. Draw the monomer of this. All right, well, remember, we've learned about addition polymerization, and these two bonds here on each side have come from a double bond in the middle of the two carbon atoms. So what we've done here is we've converted a double bonded monomer into two single bonds either side. So we just need to recreate this with the, here's our H and H, and then in here we have a double bond, okay? So you break one of these bonds here in the double, and that gets you a bond either side to create your polymer. When PVC is burned, the gas hydrogen chloride is formed. Hydrogen chloride molecules, HClG gas, contain only two atoms. Now, again, you can get a bit confused here because HCl is what we know as hydrochloric acid when it is an aqueous solution. But HCl is a gas under normal circumstances. Contain only two atoms. State the term used to describe a molecule containing only two atoms, okay? Now, the trap here is you might write diatomic element, but you just have to write diatomic. Okay, we know about the diatomic elements, hydrogen, oxygen, nitrogen, etc., and the halogens, but we are just going to write this term here. All that means there is two atoms, a molecule made of two atoms, diatomic. You could put diatomic molecule and get away with it, but that's about it. All you need to do is write diatomic. A table of some thermosoftening plastics and their melting points is shown. Okay, so what we have here is several plastics and their melting points. Okay, complete the graph to show the melting point for each of the plastics. An additional graph is found on page 32. Okay, we've got 2 marks for this. So what do we have to do? Well, we have categories. Okay, we don't have a scale here, which means we're going to be putting in a bar chart. Okay, so this is going to be bars. Right? Now, your best bet here is to get a ruler out. I'm just thinking, have I got a ruler handy? Probably not. But we want to make sure that we get this right. So here, they've put in the individuals. So what we're going to do is we have to choose the right kind of graph, and it's going to be a bar chart. What we're not going to do here is put in plot points, because that would be wrong. It's not a relationship graph. So we'll get 1 mark for doing the right kind of graph, and we'll get 1 mark for plotting it correctly, I would think. So let's have a look. POM 165. 165. Now, the other thing we have to watch out for here is 160 to 180. So there's 20 in each of these gaps. So this is going up by 20 degrees each major division. So the minor divisions are going to be 4, aren't they? So that's going to be 64, 68, 72, 76, 80. So each one of these is going to be 4. So we have to watch out for that too. So 165, 4. It's just going to be just above that line there. We're going to put it in fact, let's just put it in to the left of the bar that we want. PET, polyethylene, something. Polyethylene maybe just, is it? 260, let's go up to 260. Goes right to the top. So we'll put it in right at the top. That's okay. That goes to the top. HDPE, high density polyethylene, I guess, is 131. We need to go up, it's going to be basically halfway between these two, just slightly more than halfway. So going to be in there somewhere. PVC, you get half a box tolerance for this. So as long as you're within half a box of where the line should go, but you need to draw the lines as straight lines. So PVC, polyvinyl chloride, which is the one we've just been looking at, is 82. So we need to go up to 82, and that's, remember, each one of those bars is 4. And polypropylene, which is 130, goes up to, so is going to be halfway between those two exactly. Right. So what we need to do is get our ruler out. But anyway, that's the graph put in. And just put some shading in to show where the bars are and make sure that your lines going across the top do not extend beyond half a box beyond where they need to be. This one didn't come out very well. Let's just make that nice and neat. But anyway, as long as you're within half a box of where your line is supposed to be, you will get the marks. Okay, and you'll get both marks. That's a box, more than half a box extended. You see a little bit of pencil mark there. Okay, so that looks neat enough. And then it says, suggest why PVC could not be used as a container for boiling water. Well, let's have a look at PVC. Well, PVC's melting point is 82 degrees Celsius up here. So it melts at 82 degrees Celsius, which is below the boiling point of water. And I think it would melt, it would get you the answer. So it melts at 82 degrees, which is below the boiling point of water, and that would get you the answer. Okay, so good.